Vsauce, Kevin here, and I'm about to stretch my Winky until it snaps. Actually, I've got 3 of these anti-stress emoji people called Winkies. Only one will survive, and you will witness an incredibly simple problem that almost everyone gets wrong, and at the end, get to the bottom of one of the most famous probability problems ever. It's time to meet the Winkies. Orange, purple, and blue. They've been sentenced to death, but just one will be pardoned. The other 2 are walking the green mile, but they don't know which 2 it will be. All they know is that I, Warden Kevin, get to decide. Right now, each Winky's chance of survival is 1 out of 3. So 1/3 plus 1/3 plus 1/3 equals 1. With every Winky having an equal shot at living. There's no paradox here. Yet. The fairest, least biased way to choose which Winky lives is to put 3 slips of paper into a hat and randomly draw a color. Gotta mix around your slips, and here we go. But what if they know that I drew a color, yet I don't tell them which one it is? These Winkies would be left to wonder who will live, who will die, and what their own personal odds of survival really are.
Kevin, you can tell me. I can keep a secret. Tell me who will live.
My Winky is talking to me, and I think I recognize that voice, a keeper of internet history. How'd you end up on death row? Anyway, I can't tell you who survives. It's just not fair, and I definitely can't tell you whether you live or die.
I understand. You bear a heavy burden. Just tell me one of the Winkies that will be executed. If purple lives, tell me blue. If blue lives, tell me purple. And if I'm going to live, just choose which of the other 2 you'd like to name. Do this for me, Kevin. Please.
I don't know, Orange Winky. It really doesn't seem fair.
Please, Kevin. Pretty please. You are so handsome, and those glasses look so good on you.
Okay, what's the harm? I can't possibly give Orange Winky any useful information here. Okay. Blue will be executed. Right now! I didn't mean to put his body back that way, upside down, but you know what? Warden Kevin is a cruel warden.
Kevin, you fool. Now I know my odds are 50-50. I will live, or purple will live. There is no alternative. You stupid man. Oh, he's so dumb. And also fat.
Oh no. He's right, I got tricked by a Winky. Now there are only 2 choices. One will live and one will not. So his odds improved from 1 out of 3 to 50-50, right? Wrong, Orange Winky! You still only have a 1 out of 3 chance to live, and Purple Winky is actually twice as likely to win the pardon. This may remind you of the Monty Hall Problem, and we'll get to why that's important later. But for now, let's break down the only possible scenarios that Orange Winky faced. Remember that I can't tell Orange Winky whether he lives or dies. When I named Blue, we can compare the 2 possible outcomes after naming Blue. Scenario 1, where I name Blue and Purple lives, has a 1 out of 3 probability of occurring. Scenario 3, where I name Blue and Orange lives, has a 1 out of 6 chance of happening, since 1/3 is twice as large as 1/6. And since they're the only 2 possible outcomes after naming Blue, meaning their probabilities have to add up to 1, Purple actually has a 2 out of 3 chance of survival, and Orange only has a 1 out of 3 chance of avoiding execution. The probabilities of 2 events that appear to be equally likely just aren't, and we can't handle that. All right, it's time to reveal which Winky will live and which Winky will die. This slip of paper determines our survivor. And purple lives. Sorry, orange.
Kevin, please.
Time for you to
No, have mercy.
become history.
My body is stretching. Do not stretch me, Kevin. No. Was it because I called you fat? I am dead.
Welcome to the three prisoners problem, which is actually the Bertrand's box paradox and kind of the Monty Hall problem, but mostly the Bertrand's box paradox, which came out the same year the Eiffel Tower opened, Van Gogh painted the Starry Night, and Nintendo Kopai first started producing playing cards. They eventually made video games. In 1889, 70 years before recreational math columnist Martin Gardner started playing mind games with prisoners on their execution date, French mathematician Joseph Bertrand published Calcul des probabilités, in which he posed a paradox that became the basis, the genesis for Monty Hall and will require me to stick my Winkies in pudding. Let me explain. After making me a plate of tendies in my favorite dipping sauce, my mom secretly hid Winkies in these three large candy dishes full of pudding. One of them contains two Winkies of the same color. Another one contains two Winkies of a different color, and then one contains one Winky each of those two colors. I'm pretty sure that mom said one Winky color is yellow, but I'm not sure what the other one is. This is so much grosser than I thought it was going to be. Let's reveal this Winky's color. Oh.
Thank you for licking me clean, Kevin. Your tongue is so smooth.
How are you alive?
You can't kill me, Kevin. We're friends now.
Okay, well, clearly we have an orange Winky somehow back from the dead. And we know that the second Winky color is yellow, but what are the chances that the other Winky in this pudding is also orange? We know that the three dishes are orange, 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 yellow, and yellow, yellow. Each combination is equally likely to be chosen at the start. We also know that this can't be the yellow, yellow dish because I just pulled out the creepiest orange Winky on the planet. That means it's coming from orange, orange, or from orange and yellow, and both had the same chance of being selected. Once we pull the orange Winky, we know that the odds the other Winky in this dish is orange is 50-50 because I've clearly chosen either the orange pudding or the orange yellow pudding, right? Wrong! Again! For the same mathematical reason as our prisoner problem. This is the mathematical foundation of all these scenarios. Our inability to recognize that what appears to be 50-50 really isn't. Hold on, before I explain further, let's just find out real quick where the Winkies are because I actually don't know. Well, this was orange. Orange. Oh, so it was orange. Jar number 2. I can't even tell. That. Okay, that's yellow. Now, is this one orange or is this the yellow jar? Time to find out. Looks orange. Let's see. Yep, there's the other orange. So that was our yellow-orange, which means that this has to be the yellow. Yellow. I have to clean up this pudding or else we can't continue the video. So I'll be right back. All right, now that the Vsauce mukbang portion of our video is complete, let's get to the root of this problem. Bertrand conceived his original paradox with gold and silver coins in boxes. He had the same basic setup we used: gold, silver, and silver, with the player reaching into a random box, drawing a gold coin, and wondering about the odds of that box containing another gold coin. Once we pull a gold coin or an orange Winky or one of the prisoners to be executed, it feels like our odds of whatever comes next are an equal 50-50. We're just choosing between two leftover options that appear to be equally likely. We know the other coin is either gold or silver. But look, if you pull a gold coin, you either pull gold coin 1, gold coin 2, or 3. And at this point, you conceptually know that you're not dealing with the box with the 2 silver coins. You don't know exactly what it is, but you do know what it's not. If you choose gold 1, the other coin is gold 2. If you choose gold 2, the other coin is gold 1. If you choose gold 3, you'll get silver 1. So 2 out of 3 times you draw gold, it'll be paired with another gold. And only 1 time out of 3 will you get stuck with silver. But it's almost impossible to shake the notion of 2 equivalent options even when the math shows us that it's wrong. It's the same reason why the Monty Hall problem is a problem. The prisoner problem and Monty Hall add a story to the math and an additional third party. It seems like that would make it more complex, but it actually helps you understand the probability more easily. Adding a second player's perspective lets us see that the warden will never reveal who lives, and Monty Hall will never reveal the door with the money. Despite that additional information, we still get it wrong. Why is it so hard when the solution is right in front of our face? Probably because it is right in front of our face, and it's why very, very smart people often get it more wrong than right. I mentioned this in my What is a Paradox video, but when Marilyn Vos Savant wrote in Parade magazine that switching doors in the Monty Hall problem resulted in a 2/3 chance of success instead of being an obvious 50-50 trade, Parade received over 10,000 letters telling her she was wrong. About 1,000 of them were signed by PhDs, and she claims many were sent on official letterheads from college math and science departments. And I still get comments on my video from people all over the world telling me that I'm wrong. Massimo Piatelli Palmarini, author of Inevitable Illusions, said that no other statistical puzzle comes close to fooling all the people all the time. And research in 1995 by Gransberg and Brown found that only 13% of people correctly switched Monty Hall's doors. In a 2003 paper in the Journal of Experimental Psychology, Stefan Krauss and X.T. Wang described these particular problems, from Bertrand's box to Monty Hall, as cognitive illusions, stating that they demonstrate people's resistant deficiency in dealing with uncertainty. They found that only 3% in the control group solved the problem with mathematically correct reasoning, and that a significant problem was perspective. When participants were able to think of the problem from the perspective of Monty Hall instead of the game show contestant, or thinking as me, Warden Kevin, instead of as the prisoner Orange Winky, their chances of choosing the right pathway improved, vaulting them from simple non-Bayesian thinking into more complex Bayesian analysis. In the 1990s, it appeared that there was no way to break the mathematical illusion of Bertrand's box, the 3 prisoners, or the Monty Hall problem. Explaining the math just didn't seem to work. It turns out the math isn't the problem. We are. Uncertainty is hard for us. Changing perspectives is harder. You're watching this video because you're a smart, curious person. And by altering your perspective, you don't just dismiss a mathematical illusion that has perplexed us for over a century because you've identified its flaw. You don't just solve it, you embrace it, you absorb it, you understand it, and you ultimately use it to your advantage. You know it. And I know that I have so much pudding to eat. And as always, thanks for watching.
Pudding. Surprise.